welcome in this new video. So in this video we will be talking about graphs and some topics of it. So with no further delay, let's get started. So basically today we will first see what is the introduction and see some of the parts of some of the concepts in graphs. So let's see what's a graph. Okay, so graph is a non-linear data structure consists that has actually nodes and edges, and nodes are sometimes also referred to as vertices, and edges are lines or arcs that connect any two nodes in a graph. So it can be formally defined in this way, like a graph consists of a finite set of vertices and set of edges which connect a pair of nodes. But basically you can see that this figure represents a graph. So you can also think that it is a tree if you just remove this and this, and as well as this edge here. So it will be having 2 as its root, then 1 as its child, 1 and 3 as its child, and 0 and 4 as its leaf. So you can also convert a tree to graph by just combining two subtrees. Okay, so now let's see how many types of graphs are there. So basically there are two types of graphs. So one is an undirected graph and other is a directed graph. Okay, so what is an undirected graph? So an undirected graph is a graph that doesn't have a directed vertex, like it will contain only one path from a node u to v. Let's say if you are having this 0 and 1, then if you could only go from either 0 to 1 or 1 to 0, then it will be a directed graph. And a graph cannot be both directed and undirected, so it will be either directed or it will be either undirected. And undirected graph means if you see this 0 node and 1 node, then the edge that is connecting this 0 and 1 node will, so through this we can actually traverse from 0 to 1 as well as 1 to 0. So there is a both direction in which we can go, but in a directed graph we can go only in one direction, either from 0 to 1 or 1 to 0, like this kind of thing. So now let's see what is the time complexity of a graph to traverse it. Okay, it can be traversed in a BFS and DFS manner that I have also discussed in the trees. If you haven't seen the video, then do check it out from the I button on the top right corner of this video. So it basically takes order of v plus e time, and in the first case it generally takes order of v square for the space. Okay, then how it is stored in a data structure. So we can use either a matrix that can be known as an adjacency matrix, and we can also use a array of linked lists, so it can be called as adjacency list. So if you want to dig deep into this, then you can check this. The main thing is that for every I comma jth column, so it will be connecting the edge. If there is an edge, let's say from 0 to 1 in this diagram, so we will have 1 there for the connection of the edge, otherwise we will have 0 if they are not connected. So self loops are not always allowed if you are taking for a particular one, but we can also have those as well. But here we generally consider that we do not have self loops in the graph. Okay, now coming to the breadth first search or BFS for a graph. So it is the same as the breadth first traversal in the tree, but actually in this we can have a cycle in the graph that will not allow us to complete our BFS, because it will be continuing infinitely. Let's say if you start from 0, like 0 and or 2, let's say 2, then if you go as a breadth first traversal, so you will first go to 0, then again due to its nature you will again come to this 2 again, and it will go on and on. So for that we have to just take care of the visited nodes. So we just initialize an array that will contain which nodes are actually visited and which are not, and other things are basically the same. So in here I will just quickly show you what is the case. So let me show this illustration. So let's say you have this graph and you have a visited array kind of thing that is initialized to 0. That means none of the nodes are visited. So let's say we start from 1. So if in BFS, as you know, that we first see the adjacent elements, and for that in here we will also have a queue to traverse that one. Okay, so when you have 1, then just first push this one to the queue, and then check its adjacents. When you delete the queue, let's say as one has been in the queue, now you will pop 1, and when you will print, then after printing 1 you will just check that which were its adjacents, and what we will do is that you will just add the adjacents into the queue. So let's say you will add 2 and 3 in the queue. So when 3 in the queue will be there, now when you pop an element, that is dequeue from it. So let's say you dequeued this 2, then you will just check its adjacents and will just mark them as visited, okay, and 3 as well. You will mark for 3 as well, like this 5 will be marked. So now you have this queue like 3 4 5. So the print will be 1 and 2. Now you will print 3. So as we will have 4 and 5 in the queue. Now when you dequeue 4, so you will see that we have to mark 6 as well, and you have to insert that in the queue. So like this you will just pop then 5, and as no adjacent elements are remained that are not visited, so you will just print 6 as well. So this was just a brief like how BFS works in graphs. Similarly, DFS that was discussed by me in the trees part, so it is also similar to that. And also in here, to avoid the cycles in the graph, we do not actually we just only have another array that will store the visited nodes in here as well. And you can use this DFS to find whether a graph is having cycles or not. Okay, so in this BFS and DFS, as I told, that order of V plus E will be the time complexity. Okay, now as I told that you can use DFS to detect cycles in a directed graph. So what you can do is you just traverse in a DFS manner, that is depth first search manner. And what you will do is, if you see a back edge, so let's first understand what is a back edge is. So a back edge is an edge that is from a node to itself, that is self loop, or one of its ancestors in the tree produced by DFS. So this is known as a back edge. So if you see that when you are traversing, then it will again loop back to the first node or one of its ancestors. Then we will be having actually a cycle. Okay, so this was a simple thing. Also, if you want to do that in an undirected graph, we have to detect cycle in an undirected graph. Then what we have to do is we have to actually traverse from every node for this DFS, that is depth first search, from every node as well. And also one more thing I forgot to mention, that let's say in the BFS, that is breadth first search, if every element, if we know that the graph is not disconnected, then it's okay. But if you know that the graph is disconnected, then what you have to do is that you have to check for every node and check whether it is visited or not. So if it is not visited, then apply breadth first search again on it. Okay, now coming to one more method to actually detect cycle. So you can see this method as well, joint and disjoint sense. So basically what we do is that let's say we have this graph, and we make basically we make subsets. So if we take an edge and put their vertices in a subset, and then what we will do is we will just check if one element is already present in if we are making a subset of this 1 and 2, let's say, then is it contained in another subset, let's say 0 and 1. If it is there, so we will be having a cycle. So basically an element that is in more than one subset, then we have a cycle. So this is just a basic thing. And also we can detect a negative cycle in a graph with Bellman-Ford. So just I want to say that what is a negative cycle. So negative cycle just means that that the overall sum of the cycles will be negative. That is, if we have a weighted graph, then we will be having negative edge weights. So if we add all the weights of a cycle, and if it comes out to be negative, then it is called a negative cycle. Okay, now coming on to the strongly connected components. So strongly connected components basically means that directed graph is strongly connected component if there is a path between all pairs of vertices. Okay, so a strongly connected component of a directed graph is a maximal strongly connected subgraph. So basically if you have a cycle, then you can see that it is a strongly connected component. Also if there are path for all pairs of vertices, between all pairs of vertices, then it is a strongly connected directed graph. And the components, if you see that here we have 3 SCCs, so you can see here as well. So this is a basic thing of SCCs. Now we come to the topological sorting. So topological sorting will only be possible in a directed acyclic graph. So directed acyclic graph means that the graph is directed graph and it is having no cycle. So it is topological sorting basically means that we are linearly ordering vertices in such a way that if there is a directed edge between u to v, then the vertex u always comes before v in ordering. So if we do not have a graph that is not a DAG, then topological sorting is not present. Okay, so now let's say we are having this graph, then you can see that 5 2 0 3 4 and 1 can be a topological sort. You can also see this article if you want to go in depth and make you understand if you are not knowing in depth about this, but it's about some revision, so I am just going somewhat fast. And also we can just find all topological sorts by just actually making a DFS traversal and making a tree for those DFS traversals. Okay, and yeah, it will, if you have to once try to actually do it by your hand, so practice it, so you will get some more idea. And there is one also one more algorithm, this CANS algorithm, that will help to actually make the topological sortings, different types of topological sortings for a particular given graph. You can see this as well, but it is not that important, just concept of this topological sorting is mandatory to be known. So this was it for today, and I hope that you liked this video as well. So thank you for your time, and till the next video, keep learning and keep watching.